This Excel video is going to be a bit longer than the rest, but it's probably the most important Excel video that we cover because the Excel tricks I'm going to show you are not as intuitively obvious as a lot of the other tricks I've shown you and not as easy to do on like your calculator. So first, the assumption is that you've also watched the videos and read the textbooks so you understand the statistical concepts behind these issues. I'm just going to show you how to do this on Excel, and I've got several examples on here. First, this first example here, we're doing a left tail test and we found a z-value of negative 1.91, and we are asked to find the p-value for this left tail test. Well, fortunately, Excel can find p-values really quickly for a z-test by hitting equals, norm, because it's a normal distribution, dot s, whenever we use z-scores, it's always standardized, dot dist for the distribution. Then if we type in our number of negative 1.91, that tells us the z-score, and then we will always type in true. And when I hit enter, we'll find out that the p-value for this z-score is 0.028. If it's a right-tailed test, we need to subtract the value from 1. And so for the second example here, we've got a z-value of 2.12. I'm going to type in equals 1 minus norm.s.dist, because it's a standard normal distribution. The z-value is 2.12, and then we hit comma true. The reason we have to subtract from 1 is this function will always tell us the area to the left, and we want a right-tailed test, so we need the opposite tail. So when we subtract from 1, in this case, we find a p-value of 0.017. We've kind of done that before, though, so I want to take a look at how we find critical values for the z-test. And it really depends if we're doing a left-tailed test, a right-tailed test, or a two-tailed test. So with an alpha value of 0.08, to do a one-tailed test, we will hit equals norm.s dot, and since we want the actual value, we're doing the inverse, open a parentheses and type in the probability we want. Now notice this gave us a negative value, and the negative value is going to be on the left side. We want the right-tailed test. So I'm going to change this to a positive 1.405 is the critical value for the right-tailed test. In fact, I'm going to gray out this box because that box is technically wrong. We want the positive value for a right-tailed test. If it's a left-tailed test, we do want a negative value, so it looks pretty much the same. We do norm.s.inverse. And then we type in the probability or the alpha of 0.08. And now because it's a left-tailed test, we do want the negative value, negative 1.405. Now in the situation where we're dealing with a two-tailed test, we need to be aware that that alpha of 0.08 needs to be split evenly on the left side and the right side. So we take half of it and get 0.04. So we'll hit equals norm.s.inverse, and the probability we'll type in is 0.04, and that gives us the negative value. Since it's a two-tailed test, we actually need two answers, so we've got negative 1.75 and positive 1.75. So now we have the two values, the two critical values that cannot be passed in order to fail to reject our null hypothesis. Now the next section in your text takes a look at t-values and doing hypothesis test when we don't know the standard deviation. And this is actually more realistic to the real world. In fact, my dissertation did exactly this process here. So for each of these problems, I've set up 3 examples here showing 3 different ways we can approach the t-test as either a left tail, a right tail, or two tails. So in columns A and B here, you see I've got a null hypothesis that mu is greater than or equal to 12. an alternative hypothesis that it's less than 12. I have a sample of 8, which had a mean x bar of 10.3 and a standard deviation of 1.4. We're going to make alpha equal to 0.01, and we're going to do a hypothesis test, a t-test, to determine if there's a significant difference. Can we reject the null hypothesis? So first, to determine the type of test we're doing, because the alternative hypothesis is less than, we are going to say this is a left tail test. Then we're able to find our test statistic. Now the test statistic we know is t. T equals x minus the mean, minus mu, divided by the standard deviation of my sample, divided by the square root of my sample size. So we'll put that whole formula in here, and I'm just going to click the cells that tell us the information we need. So equals, open a parentheses for order of operations, x, or my x bar, 10.3, minus mu, we assume the mu is equal to 12 from the null hypothesis, divided by, and then in parentheses, the standard deviation, divided by the square root, SQRT, of the sample size. Click that 8, close both sets of parentheses, and I hit enter, and we have a test statistic of negative 3.43. That's pretty large. To find the critical value, we'll hit equals t dot inverse, INV. The probability we want is the alpha value. We want 0.01 in the tail, comma, the degrees of freedom, which is always the sample size minus 1. So our sample size is 8, minus 1 is 7, and when I hit enter, we find the critical value is negative 2.9, which means our test statistic, negative 3.4, went past the critical value, so we have to reject the null hypothesis. Now we could have done this an alternate way. We could have done this by finding the p-value instead of finding the critical value. If the problem asks us to find the p-value, what it's really saying is, what is the probability that I end up with my test statistic or worse, and how does it compare with alpha? So instead of doing the critical values, we could have done the p-value, which is equals t dot dist, open a parentheses, and then we take our test statistic. I just click the test statistic, comma, the degrees of freedom, 8 minus 1 is 7, comma, and then we always type in true for the p-value t-distribution. And when I hit enter, what we find is the probability that I get my test statistic or worse is 0.005. Alpha tells us the acceptable amount of probability of 0.01. Because the p-value is smaller than that, that is unacceptable, and we will reject the null hypothesis. Notice we get the same final decision, we just got at it a different way. We can either use the critical value or the p-value.
For the second example here, you'll see that we have a null hypothesis that is less than or equal to 12, and this time the alternative is greater than 12. Notice the alternative being greater than 12 tells us the type of test we're doing is a right-tailed test, and that'll be important. This time I took a sample size of 13, found a mean of 14.1, and a standard deviation of 4.6. Let's run our hypothesis test. First, to find this test statistic exactly like we did in the first example, equals, open a parentheses, x bar minus the mean, which always comes from the null hypothesis, close the parentheses, divided by, make sure you put the denominator in parentheses, the standard deviation, divided by the square root of the sample size. Close both parentheses and hit enter, and we have a test statistic of 1.64. To find the critical value, remember the calculation with the t dot inverse gives us the area on the left side. Since this is a right-tailed test, we don't want 5% on the left side. We want the other half, or 95% on the right side. So for the critical value, we will type in equals t dot inverse, open a parentheses, and the probability we want on the left side is 95%, 0.95. That'll give us 5%, 0.05 on the right side. And the degrees of freedom, as always, is 1 less than the sample size. 13 minus 1 is 12. And so our critical value is 1.78, saying we will reject anything past 1.78. Of course, our test statistic at 1.64 is not passed, so we will fail to reject the null hypothesis. Again, we could have done this instead of the critical value on these last two steps. We could have instead found the p-value and compared the p-value to the alpha. To find the p-value in Excel, we will hit equals t dot dist dot. And this time, because we want the right tail, instead of stopping here and opening the parentheses, we'll type in dot RT, and that's going to give me just the right tail of the t distribution. We're always interested in our test statistic with p-values, comma, the degrees of freedom is 1 less than the sample size, 13 minus 1 is 12, and you'll see we have a p-value of 0.06284. Comparing the p-value to the alpha, we see that p-value is larger than alpha. If that is larger than alpha, then that's okay. We just don't want to be smaller than alpha. And so we will fail to reject our null hypothesis. Let's take a look then at our third example. Our third example, this time we're going to do an equality test. The null hypothesis is that mu is equal to 12, and the alternative hypothesis is that mu is not equal to 12. Because we have not equal for the alternative hypothesis, the type of test we're doing is a two-tailed test. We have a sample size of 12, x bar is 10.1, the mean of 10.1, and a standard deviation of 2.4. And this time we're going to do the alpha of 0.1. Remember, that's a 10% alpha, not a 0.01, but a 0.10, 10% alpha. Test statistic is always the same, equals, open a parentheses, x bar minus the mean, which comes from the null hypothesis, which we assume is true, divided by, make sure you put this denominator in parentheses, the standard deviation, divided by the square root of the sample size, close both parentheses, and this time we're dealing with a test statistic of negative 2.74. To find the critical value, we can hit equals t dot inverse, and you notice there is a two-tailed test option, dot 2t, and then open the parentheses. Then we can enter in the decimal of 0.10 that we want in both tails. Comma, the degrees of freedom, 1 less than the sample size, 12 minus 1 is 11, and we get 1.79. Now, of course, with a two-tailed test, you need two critical values, not just positive 1.79, but the negative version of that. And what's really nice, to get the negative version of that, I just have to hit equals negative, and then click that cell, and it'll give me the negative version of that critical value. So I can't go above 1.79, I can't go below negative 1.79. We have negative 2.74, that's well beyond it, so we will reject the null hypothesis in favor of the alternative that the mean is not equal to 12. Again, instead of doing the critical value and making a decision, we could have done a p-value and make a decision based on that. To do the p-value with a two-tailed test is really nice. You hit equals t dot dist dot 2t for two tails grab that test statistic, comma, and then type in the degrees of freedom, which is 11, one less than the sample size. Notice when I hit enter, though, it gives me this error. This error comes up because the two-tail function requires the test statistic to be positive, and our test statistic was negative. We can fix that really easy in the formula. I click in the formula bar and just put a negative sign in front of the cell I selected and hit enter, and now it will tell me the p-value of the two-tailed test. P-value of 0.01, which is much smaller than 0.10, so we will reject the null hypothesis. Hopefully this video is going to be helpful to you as you're working on the homework assignment this week. Good luck to you, and let me know if you have any questions.